All right, welcome back, class. Today we'll discuss 2.4. This is one of the big rules from the derivatives. This is known as the chain rule. In this section, we'll discuss finding the derivative of a composite function using the chain rule, finding the derivative of a function using the general power rule, and then simplify the derivative of a function using algebra, and find the derivative of a trig function using the chain rule. So I want to establish this from the beginning. We already have a rule for power form of functions. We already have a rule when you multiply by a constant. We already have a rule when you have a sum of two functions or a subtraction of functions. We already have a rule for product of two functions, and we already have a rule for division of two functions. Well, if you guys remember from algebra, we also have another type of operation of functions, and that is composite. Composite functions deals when you have a function inside a function. Well, when you have that case, we have a rule for that as well. The derivative rule for that is known as the chain rule. And so here is an example of the two types of problems that we have seen before. So on the left side, we didn't have to use the chain rule because there was no function inside a function. It was in fact, we only had to use the power rule, the sum rule, and then the constant rule. For this one, we only had to use the trig rule, the trig function rule. For this one, we also had to just use power rule, the sum rule, and then the constant rule. For this one, we only had to use the power rule, the plus rule, and then the trig function rule. Well, if you guys notice, in this example, we end up having actually a function inside a function. Now, I can make this obvious for you guys by writing this in a power form, which you should always do, right? Whenever you're dealing with derivatives and you have a radical expression, you should automatically do the habit of changing this to power form. If you notice, there's an inside function, and I'm going to highlight this. This is the inside of a function, and the outside function happens to be just a power form, right? It happens to be a power form, the power of 1/2. That's the outside function. We're going to play around with that concept more in a second. So here's another one, right? The sine of 6 of x. Well, 6 of x is the inside of this function, and I'm going to highlight it. This is the inside, right? Sine is the outside function. So you have inside this sine function, instead of just having x, you have an actual function known as 6x. Another one that we have here is the next one, which is 3x plus 2 to raise to the power. So here is your inside function. 3x plus 2 is the inside. Versus in the other case, we didn't have that. There was no outside power. So the power becomes the outside function. And then in this example, we can rewrite this as x plus tangent of x squared. We can see here clearly that this is the inside function of the tangent. Now, in this process, in this type of technique, if you guys notice, it's very important for us to recognize what is the inside and what is the outside. And the best way to think about this is by using parentheses. I know that sometimes the expression does not have the parentheses that would help you visualize it, but this is where you have to practice. You should be able to go out of your way to put these parentheses to be able to recognize this. Now, that's part of the mathematical notation that we should try to be familiar. Now, how do you get familiar with anything? By practicing. The more you see it, the more familiar you become. So my recommendation is when you get stuck with a notation, like you don't recognize what that means, mathematically speaking, right? You don't know what that means, then try to find out what that means, right? And write it out, and then record it, put it somewhere where you have your notes and things to remember. Also ask if you have the book right there, then that might be just one thing that you can just check, but also you can check with me, you can check with your classmates. And it's important for us to know these rules. So please write them out somewhere. Things that you need to remember, have it in your room to be able to visualize it every single time. So in the next example, we're going to talk about the derivative of a composite function. And we're going to use the concept of a gear to do this. So a set of gears is constructed as shown in the figure below, such that second and the third gear, so here's your second gear, and then here's your third gear right there. So second gear, third gear are in the same axle, so they have the same axle. So that means if the third gear rotates, that means the second gear rotates. Let's see, as the first axle revolves, here's your axle right here. If you revolve this axle, then you're gonna move this gear, right? It drives the second gear, right? Because it's gonna move the second gear, and that gear is gonna act on this axle, which is gonna move this gear, which is gonna move this gear, which is gonna move this axle. So if you guys notice, there's a connection between this axle, that axle, and that axle. So let y, u, and x represent the numbers of the revolution per minute of the first, second, and third axle, respectively. Find dy du, du dx, dy dx as shown, that this equals that. Well, we already know, they're already giving us a few things, right? They're saying that on the first axle, we have the first gear, right? Or we have this gear right here, and this is going to be moved, and we can measure the movement of this gear by revolution, meaning it takes one whole revolution, right, to be able to rotate this whole axle. The same thing with this, right? It requires the whole gear to move one full rotation to be able to move this axle. So y represents the number of revolutions per 1 minute. U represents the number of revolutions for the second axle per minute, and then x represents the number of revolutions of this axle per minute. And so what we're hoping to find is this, right? We want to find dy du, du dx, and dy dx. Now what do those mean? Well, dy du, remember that dy is the change of y, and then du is the change of u. Well, I remind you guys that derivatives are a rate of change. So this is the rate of change of the first axle, right? Because y represents the first axle with respect to the second axle. So then that means we're going to find those numbers, and we're going to do that in a second. So what is du dx? Well, du is the rate of change of the second axle, as it's stated right here, second axle, with respect to the third axle, as seen here. And we're going to find those numbers in a second. And then dy dx is the rotation of the rate of change of the first axle with respect to the third axle. So we want to see how this is affects this, right? Or how is the relation between those two. So first of all, let's talk about rotation. What is a full rotation? Well, we have a circle, right? That means that you have to go from the one point of the circle has to have moved all the way around. Well, that will depend always on the circumference, right? So we can see here that if we have this, if we let this circumference be C1, which is the circumference of axle 1, then we all know that it all depends on its radius, right? And I'm going to call this radius 1. And so we have 2 pi r is the radius of this axle. Well, what about what about the circumference of 2? Well, maybe if I draw here one more, let me try this right here. Let me try one more. For the circumference of R2, we will have a different radius, right? A different radius. What we know in this radius is that the radius for the second gear, right, is actually 3, right? Which is, and compared to the radius of gear 1. So if I want to write this, rewrite this gear, this radius in terms of this radius, I'll just have to say this is 3 times. This is 3 times. the radius of the first one, right? And so we can say here that if we do some basic algebra, we can move this 3 to the front without multiplying into 2, so we can see a pattern here. If we multiply this to the front, the 3 to the front, and we collect and group 2 pi and r1, then we end up getting this relationship, right? And this relationship suggests that the circumference of gear 2 happens to be 3 times the circumference, right? If you guys notice, this is, you guys recognize this is circumference of gear 1, so it's 3 times the gear 1. So the circumference of gear 2 happens to be 3 times the circumference of gear 1. That means that it takes to move gear to rotate gear 1 3 times to be able to be equivalent to the circumference of gear 2, which means that when the axle 2 when axle 2 makes 1 revolution, axle 1 needs to make 3 revolutions. So see how we were able to connect the axles between those two? So what we're saying here is the rate of change of the first axle needs to do 3 rotations to make 1 rotation of the second axle. So we found that this gives us a relationship of 3. So do you guys see how we just did number of rotations of axle 1 over number of rotations of axle 2? In a similar way, we're going to do that for the second gear. So for the second part over here. So in this example, we have this we have gear 3 and gear 4, right? We have gear 3 and gear 4. Well, in this example, we want to make sure we understand these two axles. So if you notice and we compare these two, notice that this has a radius of 1 and this has a radius of 2. Using a similar argument that we had over here, we're going to have that it's going to require 2 rotations of gear 3 to be able to make 1 rotation of gear 4, meaning that it's going to require 1 rotation of axle 2, 2 rotations of axle 2 to make 1 rotation of axle 3. So in a similar argument, we can say that axle 2 makes 2 revolutions, then that means the axle 3 needs to make 1 revolution. So when we said over here dy over dx, the rate of change of the first axle, over here, the rate of change of the second axle with respect to the third axle is you need to make 2 rotations on the second axle to make 1 rotation of the third axle. So that means that we have 2 over 1, which implies we have 2, right? 2 over 1. And then we're going to use that same argument over here, right? So the good thing about this is that in the main question they were asking us, can we show that these two are the same, that these are related? Well, yeah, right? Because if you change the rotation here, you will affect the rotation here, which is going to affect this axle, which is going to affect this rotation. So there is a connection between moving this one and moving that one. So the rate of change of the first axle with respect to the third axle can be described as dy over du times du over dx. Well, all we have to do is replace dy du with 3, which we already found it, and then du over dx with 2 over 1, which we have 3 over 1, 2 over 1, 3 times 2 is 6, and 1 times 1 is 1. So that means that to change the rotation here, the rate of change of the rotation of the first axle with respect to the third axle will be that you need to make 6 rotations of the first axle in order to make 1 rotation of the third axle. So this is a great example where we can see here the benefits of gears, where we can simplify the process. Now there is, you notice here that if you work backwards, if you make one rotation here, what you're doing 6 rotations here. So you can use it both ways, right? Depending on the mechanic structure you're trying to work on here. So, all right, moving on. So let's define what's a chain rule. So I already mentioned a few things here, right? A chain rule is taking the derivative of a function that has a function inside. So you will see a composite function. So think about composite functions in this case. So you're trying to find the derivative of this, and then sort of the concept of that happens to do with what we just did upstairs. So you're taking the derivative of y in respect to x, knowing that there is a function inside of y, right? So and that function meaning u. So in a way, you can think about it as like you're taking the derivative of the outside in respect to the inside, and then taking the derivative of the inside and multiply by the derivative of the inside in respect to the x. So this is actually more, this looks more like this. So the derivative of this composite function suggests by the chain rule that you take the derivative of the outside function, leaving the inside the parentheses the same, and then multiplying, like product right there, by the derivative of the inside. Let's look at an example here. Now in the first examples here, we can there's a benefit of looking at this problem in terms of u, because as I mentioned before, the easiest way to play this game is to recognize what's the inside and what's the outside function. If you guys notice here, point out here, I have a figure here that says if you have a y equals f of g of x, right? This is the inside function, this is inside the f function. You can let that be u and think about this as being the inner function, and then f as the outside function. So when you're taking the derivative of this, you're going to take the derivative of the red function first, and then multiply by the derivative of the outside. So here, do you see how that works out? Derivative of the outside, leave the inside as it is, multiply by u prime. Now, where does this rule come from? You guys know where this rule comes from. When we can actually, you guys have the tools to be able to actually find it. All you have to do here is use the actual definition, the derivative definition of the limit as h goes to 0 of f of x plus h minus f of x all over h. Now obviously in this example you have to adjust because we have a function inside a function, so the process will be a little more technical, but the idea is that it comes from this definition. Now the rule makes everything much easier. You don't have to do this limit over and over again. Now we have a rule that we can just jump into it. So let's first begin. We're not going to do derivatives right now. We're just going to begin by recognizing these types of functions, composite functions. Again, what I mentioned before, the game of those students who can recognize that this is a composite function and thus you have to use chain rule will be ahead of the game, right? A lot of the problem in this class is recognizing which rule is needed. So how do you know which rule is needed? Well, you have to know that you're multiplying two functions, right? Or you're dividing two functions, or you have a power function, or you have, in this case, a composite function, a function inside a function, right? So let's point out some of these things right here. So you have y equals 1 over x plus 1. Seems kind of normal. Well, this is actually a composite function. So this is the inside part. And if you guys notice what I did here, I put it in parentheses to make it more obvious, right? If we look over here, if we are trying to break this into, we're using the u to make it more obvious for the reader, for you guys right now that you guys are starting, is you let u be x plus 1, the bottom part of the function. If you let that be x plus 1, what do you guys see here? That now you can write the original function as 1 over u, and you guys know what to do here, right? You guys know what to do here. If I ask you to find the derivative of this, you guys know what to do here. This is the outside. This is the inner function. All right. So we'll put everything together. We're just right now trying to help us visualize inside versus outside. So let's look at the next one. Y equals sine 2x. Y equals sine of 2x. First of all, a lot of students don't recognize that 2x is inside this sign. So what I'm doing for you guys is make sure that you guys practice recognizing that notation. So if you guys need to go out of your way and put parentheses, go ahead and do that. So that's your inner function. So I'm going to let u be 2x. And then if you guys notice, sine is the inside, sine is the outside, u is the inside. Let's look at this one right here. So here we have a square root function. This is, if you guys hear what I said, this is overall a square root function. So that means that the inside of the square root is this, right? And I'm putting in parentheses to make it more obvious, right? So if I let u be 3x squared minus x plus 1, that means the outside function will be this square root function. And you guys know what to do here, right? We know that we will have to change this to power form to be able to take the integral, the derivative, sorry. If we have tangent 2 of x, we already know, I already mentioned this a few times, right? But you also know this one trick, that this is equivalent to say that the square of a tangent, right? You're squaring the entire tangent. First you take the tangent of it, and then you take the square. So making this more obvious, tangent of x is the u is the inside part, and then the square is the outside. So that actually tell us something about in a particular example of chain rule. And that particular example, this is a consequence of chain rule, and that's just one scenario, right? The scenario where you're dealing with a function inside a power function. Do you guys see that? Y equals u of x to the power of n. So this right here is your inside function. What happens when you do that? Well, again, this is one consequence, right? One consequence of this chain rule. What they're saying here is that because we're going to be doing this so many times, this chain rule example, it's worth giving it a name, right? And we're going to call this the general power rule. So we have u of x, right? To take the derivative of this whole thing, what we're going to do is we're going to take the power. We're going to do the derivative of this by taking the power in front, right? Just like we did it before, right? Multiply the power, right, by, and then we're gonna, instead of multiplying just by x, we're going to multiply by the inside function. This is the inner function. Just multiply by the inner function, and then take away 1 from the power, and then multiply now by the derivative of the inner, right? So here is where you take the derivative. So if in this part, if you guys notice, we took the derivative of the outside, leaving the inside, the inner the same, and then multiplying at the end by the derivative of the inside, or the inner, right? So that's the name of the game. So you can see that it's equivalent to saying this, u to the n, right? So bring down the power, copy paste the power, right? N times u multiply raised to the power of n minus 1 by taking 1 power, right? This is power rule. And then the inner function will take the derivative of the inner function over here, right, by multiplication. So here's a few examples. So example 4, apply the general power rule. Find the derivative of f of x equals 3x minus 2x squared to the third. So first, recognize what's the inside and what's the outside. So I automatically, when I see this, one of the hints that I have, or one of the techniques that I have just for practicing this for 1,000 times, right, is I recognize the inside function because it's inside parentheses usually. So that usually gives it away. So right now, this is telling me that this must be my inside function, and it is. So I'm gonna let u be 3x minus 2x squared. So that means if I replace that from the function, we're gonna have just f of u equals u to the third. So do you guys see here that the outside function happens to be a power, versus the inside function here happens to be just regular polynomial, right? Which we know it's going to be power rule, sum, and so on, right? So my strategy would be, and right now I'm doing more steps than I usually do. Actually, a lot of these steps I can do in my head, and you guys will do that at some point. Not right now. Right now, you guys need to go out of your way to write every single note, so you can develop the skills of be able to read the notation and be able to recognize every step of the problem, right? So if I take the derivative of f of u, right, and I'm taking the derivative of the whole thing, then that will be the derivative of the outside, right? You see how I put the mark right there? That means that this is the derivative of the outside, leaving the inside as it is, multiplying by the derivative of the inside. So if I do that, right, if I do the derivative of the outside, that will be obviously the derivative of using power rule. So I'll multiply 3, right, the power of 3, right, it becomes a factor, multiplied by u, leaving the inside the same, take away 1 from the power, so it becomes a 2, and then multiply by derivative of the inside, right? That's the plan. So if you guys notice, that's sort of what I'm going to be doing here. So usually we don't do this line, but I just did it so you guys can kind of see how u is played in this process. So the derivative of f, right, is going to be the derivative of the function, right? So I haven't done anything, I just set it up. So to take the derivative of the whole thing, I'm going to take the power, multiply by the inside of this, the inner part of the function. So I left it, I copy and paste it, right? I didn't do anything to this, right? I have to actually put it there. Then, and then take away 1 from the power, and then multiply by the derivative of the inside. That's when you deal with the inside, right? Here you just copy and paste it. Here you have to take the derivative of it. And followed by, now everything is good except that we just have to come back and finish this part. So 3 times, leave the inside as it is, put the 2 there, and then take the derivative of this. This will be 3, this will be negative 4x. And there you go. So that's it, right? I apply the derivative of the outside, multiply by the derivative of the inside, and then I just finish the next my last note here. So that's how we do this. Now, do we always have to use chain rule? Some occasions you don't have to. In this example, I could have expanded this whole thing and then use algebra to expand it, and then use the power rule at the end. But a lot of times this can be very, very complicated or time consuming if you do it by simplifying first the expression. And there's some examples where you can't algebraically simplify it. You actually have to use chain rule. So it is something that we must learn in this class. There's no way around it. Just like product rule and quotient rule are also rules that you can't go around it. All right, so here's another example where we're gonna combine other rules along the way, and so to find such derivatives. So find the derivative of f of x, where f of x is equal to x squared times the square root of the quantity 1 minus x squared. So what do we see here? If your spider senses are saying that we have to be using product rule, then you're already thinking like a good mathematician. So first think about which rule you're going to be using, right? So let me separate this into 2 boxes here. So I see here this being multiplied by this, right? I don't have to put a dot there to tell you guys that this is multiplication. It's already assumed it's multiplication because of the parentheses, right? So I don't have to have that there. This is already assumption that it's a product. So I'm gonna say here, we're gonna start the big picture, right? This whole big picture, right? The big picture suggests that we have to use product rule, right? That's how we started this problem, by using product rule for the big picture. Now along the way, because we're using product rule, we know that we have to take the derivative of one of the factors. Now yes, along the way we're going to have to take the derivative of this, which suggests that we have to use chain rule along the way, in some place. Now if you guys notice also that I automatically changed the square root into a power form. I remind you guys again, I mentioned this before in a previous lecture, that you should automatically change any radical expression into power form when you're dealing with derivatives, because there's no such rule for radicals, only for power rules. But we know that we can always change any radical into a power form. All right, so here we go. Here is the problem. Here's the problem, f prime of x. We're going to take the derivative of the product of this function, right? We haven't done so. I just set it up. And then now we apply product rule. So the first one stays the same, multiplied by the derivative of the second one, plus take the derivative of the first one, multiplied by the second one by itself, right? So x squared is going to be x squared. The question is, what is the derivative of the second function, right? So my recommendation here is to do some side work. Side work will help you organize your problems, minimize writing too much, and help you organize your thoughts. So I'm taking the derivative of this one right here, right? Of where is it at? Yeah, I'm taking the derivative of this, right? And it's going to be this. So I'm going to do it over here on the side. 1 minus x squared to the 1/2, close the bracket, prime, right? So here we have to use which rule? Well, we have a function inside a function, right? So 1 minus x squared is my inside function. So the outside function happens to be the power rule. So what does the power rule say? Bring the 1/2 down, right? Leave the inside the same. Leave the inside the same. Take away 1 from the power. Take away 1 from the power. Maybe I'll put this like this. And then multiply by the derivative of the inside. Now take the derivative of the inside, right? And then I'm going to put this with blue here to remind you guys that we have to take the derivative of this. And that's it, right? Now you just have to come back and take the derivative of 1 minus x squared, and then that's pretty much it. So the first part stays the same, right? There's nothing you got to change here. But the derivative of this is going to be 0 for 1 and negative 2x for this. Now that's your derivative, right? And then if you notice, because this is all product, we can simplify the 2 factor with the 2 denominator. So those cancel each other out, and now you have negative x multiplied by 1 minus x squared to the negative 1/2. So I'm going to copy and paste that into the problem, and you guys can kind of see that in here. So this right there is the derivative of this, right? So I'm coming from here, the derivative, to now writing its derivative, right? There you go. Followed by the derivative of x squared, which we know is just 2x, multiplied by the original function of the second function, and that's it. This is the derivative here. This is the derivative. So I'm gonna put a happy face here. We have found the derivative, but this is not good enough. We're gonna have to actually simplify this. So we're gonna have to simplify this. Now it requires some algebra that we need to master, especially for chapter 3. So please, let's make a good effort to refresh our algebra, review our algebra. So if you guys notice, what I'm gonna do here is I'm gonna remove some of this highlights, right? And I'm gonna keep my happy face here. What I want you guys to think about here is that there are two terms in this expression. Two terms, right? There's two terms. Now those two terms have common factors. If you notice, the common factor that they have is 1 minus x squared. 1 minus x squared. With the caveat that this has 1/2 as a power and this has -1/2 as a power. Well, I remind you guys that whenever you have terms and they have common factors, you can always factor out from the expression. Let me show you what I mean by that. So if I have x squared a plus bx to the third, and I ask you, can you guys factor this out? What would you guys do? Well, I see that both terms have an x squared as a factor and an x cubed, so I can always factor the least amount of it, right? The least amount of it. So if I factor an a, an x squared, then there's only an a left behind. And if I factor an x squared from here, there's going to be only one x left behind, right? So the idea was that we can always factor common factors by factoring the one with the least power, right? Well, this is the one with the least power, -1/2. So I'm going to factor 1 minus x squared to the power of -1/2. That's what I'm going to factor from both of them. Now, if I factor that from the first term, what's left behind? And then let me just erase some of the okay. If I factor this 1 minus x squared to -1/2, then what happens is that this goes away. I remove this whole thing. I remove this whole thing from this factor. So what's left behind? This and this, right? Negative x times x squared, which gives you x cubed. Now, if I factor this part from this term, then what's left behind? Well, I'm not factoring the whole thing. I can only factor -1/2. Then what's going to be left behind is going to be a 1. A 1. So this is an imaginary 1 there with a 2x there. Now, how do you know that's going to be a 1? By going backwards. Notice that when you multiply this back, when you multiply factors, you have to add the powers. So -1/2 plus 1 gives you 1/2. So in a way, it's like you're adding whatever's there to this, right? Anyways, and that's just algebra, right? And then we can kind of distribute here this 2x, and we end up getting the outside factor minus x cubed plus 2x minus 2x cubed. Combine like terms, that gives you -3x cubed, 2x, and then because this one has negative power, this is going to become a denominator for this function. So we move this to the bottom part and change the sign of the power, and then I can factor an x from the top, and then change this to radical form, and that's how we got this. So please try this. Try to practice this factorization. This is going to become very important. Right now, it seems like we have a lot of things on our plate because we're learning a new rule, but it's important for us to be able to do this. All right, here's another example. Let's simplify by factoring out these powers. Find the derivative of this. So the expression is in radical form, so I'm going to go ahead and change it into power form. So we see here that I have f of x equals to x over x squared plus 4 to the 1/3. Now the bigger picture here, the big picture implies that we're going to have quotient rule. So let me say this here. In the big picture, we have a function over a function, so we have to use quotient rule, right, in the bigger picture. So when I take the derivative of this, we're going to follow the quotient rule in the big picture, right? So we have low times d high minus high times derivative of low. Square the bottom, and there you go. So if you guys notice, I set out the plan here. It's easier now because I don't have to focus about the rule anymore. I already have it set up. I just have to come back and rewrite everything, but now with this as a derivative and this as its own derivative. So this part is going to be easy. That's just going to be 1, followed by x, followed by the derivative of this. We can do this in our head, right? We can have 1/3, right? The derivative of this will be, take the power and multiply it here, right? 1/3 times the function x squared plus 4, subtract 1 from 1/3, that's negative 2/3, multiply by the derivative of the inside. And let me highlight here that this was the inside part. That's your inside, right? And this is the derivative of the inside, right? At the end, you multiply by the derivative of the inside. And now we're gonna go ahead and simplify. What happens on the left side here? Nothing. It's just being multiplied by 1. What about here? Well, you have a 2x, you have a 1/3, and you have an x. So the x is multiplied to be x squared. The 2 and the 1/3 becomes 2/3, and then you still have this factor there. Now again, we have this factor. Of x squared plus 4. This is to the 1/3, and we also have another factor, x squared plus 4 to negative 2/3. We have two factors from these two terms, right? And I'm going to highlight these two terms. Here you see the minus in front of it. That's what separates the two terms. So again, I'm going to factor the least common factor from both of them. The least common factor will be obviously the one with the negative power. So I'm going to factor that out so you guys can see in the next line. Oops. I'm factoring, x squared plus 4 to negative 2/3 from both terms. Now, if you guys notice, I'm also factoring the 1/3 because I don't want to have a fraction on numerator. So I'm factoring the 1/3 as well. So to factor this out, when you factor the negative 2/3 from here, it's basically going to be a 1 here, right? It's going to be a 1. And that is because if you multiply this back here, you must have a number here that when you add them together, 1 plus negative 2/3, it should give you 1/3. So that's going to be a 1. Now there is a 3 there because we want to make sure that we are able to factor the 1/3. Because if you think of it backwards, 1/3 times 3 will give you 1. So that's how we get and we need a 1 there. So I'm thinking ahead there. And then minus the 2, the 1/3 is left, is taken away. The x squared is kept, and then this is removed. Now this technique that I just did is very, very, very common. That we're going to be doing this a lot of times. So please, please, please focus on recognizing how to factor these powers. So now that we have factored it out, this will go to the bottom part and the next line, and then we can distribute here, and you guys will see how this is very easy to simplify. It's one of the benefits of doing this. So 3x squared plus 12 minus 2x squared. Combine the x squares, and that will give us 1x squared plus 12. On the bottom part, this becomes, in the denominator, this becomes a product of the denominator. The 3 is a product, and then we have x squared plus 4 to the 2/3, and multiply those together. When you multiply two bases, you basically just add their powers, and that's 3 times x squared plus 4, 2/3 plus 2/3 is 4/3, and that's it, right? Next one, we have the last problem. The next problem is doing the same thing, finding the derivative of this expression. If you guys notice, we have a inside function and a power form. So let's recognize first what is the inside function. The inside function here is this, and the outside function is the square. So overall, basically what we have is power rule. So here we're beginning by using the general power rule. And that is that we bring the power, we copy the power, multiply by the inside, and then multiply by the derivative of the inside, and then we'll do this part in a second, right? We'll do this part in a second. So let's do that on the side. That's where we're gonna do that over here. So derivative of this becomes a different rule, right? In this case, we have to use quotient rule, right? So in the bigger picture, we started with general power rule, but within some of the layers of the function, we have to use other rules, in this case quotient rule. So let's go ahead and do that. So it will be low d times derivative high minus high times derivative low, square the bottom, there you go. Low d high minus high d low, square the bottom, and there you go. Low d high minus high d low, square the bottom, and there you go. Low d high minus high d low, square the bottom, there you go. And remember that it's important for us to actually follow the order because there is a minus in here. Alright, so the first one stays the same. The second one, the derivative of 3x minus 1, the derivative of 3x is 3, the derivative of negative 1 is 0, so it's just 3 plus 0. Followed by the minus, followed by 3x minus 1, followed by the derivative of x squared plus 3, which is just 2x, right? And then multiply and distribute and simplify. So distribute that will give us 3x squared, 3 times 3 is 9. Distribute the 2x and the negative, so negative 2x times 3x gives us negative 6x squared. Negative 2x times negative 1 is positive 2x, and then combined like terms gives us negative 3x squared, followed by a 2x, followed by a 9, all over x squared plus 3 squared. So we're going to copy that into the expression here. Let me put that in blue. So this whole thing is this, right? So when you go back over here, this becomes this part right there. And then pretty much just simplify this by multiplying numerator, denominator. So they're the same factor. So when you multiply the same factors, the same bases, you add their power. So that's how this became a cube. So do you guys see here that we have to recognize first what is the bigger picture, right? What kind of big picture we have. Big picture determines your strategy that you're going to begin with. But along the way, this may change with other rules that you have over there. So let's move on to trig functions, right? Similar argument that we're going to have with trig functions. I remind you guys that the derivative of sine is cosine, the derivative of cosine is negative sine, the derivative of tangent is secant square, the derivative of cotangent is negative cosecant square, the derivative of secant is secant tangent, and the derivative of cosecant is cosecant cotangent. Now, what we're saying here is that if you have a function inside a function, right? If u is the inside function, then what you're going to do is the derivative of the outside will be cosine. leave the inside the same, and then multiply outside by the derivative of u. Do you guys see that? So two things. The what's inside the sign is your inside function, and then at the end when you multiply by derivative, that's going to be outside the cosine function. It's no longer inside this cosine, right? It's outside. It's a product of the cosine, not a product of u. Hopefully that's clear. So let's look at a few tricks here. So when we have y equals sine 2x, right? Now this is one of the things that I keep telling you guys. Recognizing what the notation means, right? So sine of 2x, it's better if we actually see it with parentheses, right? So you could put some parentheses here and say what this is trying to say is that this is sine of 2x. So the x and the 2 are inside the sign, right? So you don't have to put the parentheses, but this is how you should be able to visualize it in your head. So what I'm saying here, then this example, this is the inside. So first take the derivative of the outside, right? Derivative of the outside is this. The derivative of the outside is cosine, and what do we do with the inside? Leave it the same, right? But then come back and then finally multiply by derivative of the inside. Do you guys see that? So at the end we'll do that. I like doing this. If you guys notice, I like doing this because it kind of helps me set up the problem, right? And so it requires me to do this in 2 steps, but it's logically correct or mathematically correct. All right, so cosine of 2x, you don't have to do anything here. All you have to do is come back and just do this part. The derivative of 2x is just 2. So move that to the front, and that gives you 2 cosine 2x, right? Next one, cosine of x minus 1. Obviously x minus 1 is the inside of the cosine, so this might be a little easier for us to visualize. This is the inside. Sorry, I mean that's the outside and this is the inside. The derivative of the outside, it's this one right here, right? Negative sign. The derivative of cosine is negative sign. Leave the inside as it is, and then multiply by the derivative of the inside. Alright, so this part is already done. All we have to do is just multiply by this, right? The derivative of that is going to be 1. So then all we have to do is just multiply the 1 in front of it, and that's pretty much it. Let's try another one. If it helps, put some parentheses there, like I did here. Tangent of 3x is tangent of 3x, right? Parentheses are there. So we're going to go ahead and plug in, we're going to highlight the inside, highlight the outside, right? So the outside function is a tangent function. So the derivative of a tangent is secant square, right? Secant square. And then what do we do with the inside? Keep it the same. Multiply by the derivative of the inside. So all I have to do is come back and multiply by derivative of the inside. So this stays the same. Come back and multiply. You just have to execute this part of the problem. So the derivative of 3x is 3. So we can move this to the front, and that gives us 3 secant square of 3x. Now I remind you guys that this is something that maybe students may erroneously think of when they look at sines. For some reason, right, students think that this is a product, right? Sine of 2x is not a product. Tangent of 3x is not a product. Cosine of x minus 1 is not a product. This is not a product. This is actually a function. This is a so when you're dealing with this, you're not thinking about product rule. This is actually a function inside a function. This is a special type of notation that we use for functions, right? This is the inside of the sign. So it's not a product. It's not a product. All right. So here's a few examples that we can try that we want to think about, and sort of I'm trying to cover all the cases where we see parentheses. When we have cosine of 3x squared, you should be able to visualize it this way, right? I don't have to put the parentheses, but this is how this is translated in my head. So I see here that this is the inside function, outside function. So we begin by the outside, doing the outside function. The derivative of cosine is negative sine of the inside multiplied by the derivative of the inside. So 3x squared becomes 6x, and then multiply that in front of the sign, and that's pretty much it. What about this one? Well, in this example, it's kind of neat because we can see here that these two actually, because of the parentheses, this actually is a constant, right? And the x squared is not inside this cosine, so therefore this is actually a constant and a function. So we use just the constant function rule, which means leave the constant as it is and then multiply by the derivative of the function, right? The derivative of the function. So the derivative of x squared was 2x. Leave the constant it is, and then you can move this to the front, and that's what we got, 2 cosine 3 of x times x, sorry. Next one, we have cosine of 3x squared. This square belongs to the 3x. So I made this bracket to make it more obvious. So here what we have, it's interesting because we have an inside function right there, and we have an outside function, right? Just like before. So you guys will see something that we're gonna have to do along the way. But the bigger picture says that we have to use chain rule. So we do the derivative of the outside. The derivative of cosine is negative sine. Leave the inside as it is, and then multiply by the derivative of the inside, right? Now, when we are doing the derivative of the inside, the rest stays the same, right? The derivative of this here, the derivative of 3x squared, well, if you notice, you have a function inside another function. So we have to use chain rule again. So here, let me put a mark here. Chain rule. Or in other words, the general power rule, right? So bring down the 2, leave the 3x as it is, take away 1 from the power, and then multiply by the derivative of the inside. So let me do that here. Multiply these together. That gives you 2 times 3 times 3 gives you 18. Move that to the front, and that gives you negative 18x sine of 3, the quantity 3x squared. All right, so it is common sometimes to do the chain rule within the chain rule. So here we have another example where we have a cosine square of x. Now I remind you guys the notation, what this means, right? It's kind of a special notation that we have. This means that the whole cosine is being squared, like this. So that's how you want to visualize it. So when you're taking the derivative of this, we're gonna have to use chain rule because we have now the cosine. Now in this example, the cosine is the inside. So we're gonna be using here the general power rule. So that means first deal with the power. So bring down the power, leave the inside as it is. Here's the inside, and then multiply by the derivative of the inside, right? So 2 cosine of x, multiply by the derivative of the inside, which is negative sine of x. Multiply that to the to negative with a 2, negative 2 cosine of x, sine of x, and that's it, right? And then here, what we're going to be using is convert that into power form, the square root. Remember, we always said change that to power form. And so now we have here that cosine of x happens to be the inside of this power form of a function. So we're going to use here, again, the general power rule, which is a consequence of the chain rule, right? Where we have bring down the power, so or copy paste the power, right? 1/2 multiply by the inside function, subtract 1 from the power, and then multiply by the derivative of the inside. And then simplify. So we have 1/2 cosine of negative 1/2. The derivative of cosine is negative sine of x. And then because we have negative power, we're going to bring that down along with the 2 there. So we have on top negative sine of x all over 2 times cosine to the 1/2, which is going to be, can be written in the form of a square root. All right. So I hope this is helpful for us to be able to recognize, be able to do the chain rule. And here's a quick summary of what we have seen so far. We have a constant multiple rule. We have the sum or difference rule. We have the product rule. We have the quotient rule. We have the constant rule, the simple power rule, the sine, tangent, the secant, cosecant, cotangent, cosecant, cosine, and then the chain rule, and then we have also the general power rule as well. So, and remember, all these rules are not made up. They actually come from the actual definition of the derivative, the one with the limit, right? The limit as h equals to 0 of fx plus h minus f of x all over h. That's where this is coming from. So they're not made up. They actually come from there. So they actually follow from the original definition. All right, I hope this is helpful. Please make sure, remember to read your lecture notes before coming to class, and then watching the video and reading your notes again. All right, I'll see you in class.